Hey everyone, and welcome to this explainer. One of the most absolutely fascinating, but honestly kind of frustrating things about our universe is just how mind-bogglingly huge it is. When you really think about it, humanity is, for all practical purposes, completely trapped right here in our own galaxy. But what if we weren't? Today we're going to decode the actual real-world physics behind cosmic shortcuts. We'll be exploring what it takes to bend the very fabric of space, diving deep into wormholes, white holes, and separating the science fiction from scientific fact.
So here's our roadmap for today. We'll start with the cosmic distance problem, move into bending the space-time mesh, and then examine the anatomy of a wormhole. After that, we'll look at the white hole exit, weigh in on the great debate of entropy versus information, and finally look at how we take all of this from theory to reality. All right, let's jump right into Section 1, the cosmic distance problem. To really get why all this theoretical physics stuff is absolutely crucial for our future, we first have to highlight the daunting and frankly somewhat depressing scale of our universe. Okay, let's dive into this number right here, 94.5 billion. To give you an idea of the scale we're dealing with, the Andromeda Galaxy is our closest galactic neighbor. If we were to board a conventional spaceship today, traveling at a pretty standard speed of about 28,000 kilometers per hour, it would take us a staggering 94.5 billion years just to reach it. That makes interstellar travel for any single human completely, entirely impossible with our current methods. And get this, even if we were to invent technology tomorrow that allowed us to travel at the absolute cosmic speed limit, I'm talking the speed of light, we are still looking at a 2.5 million year journey. Standard travel, no matter how incredibly fast we engineer our engines, is just not a viable option, period. If we ever actually want to leave the Milky Way, we need a shortcut. Which brings us to Section 2, bending the space-time mesh. This signals a huge shift in our understanding, moving from a practically impossible travel problem to some seriously brilliant theoretical solutions.
Way back in 1915, Albert Einstein published his theory of relativity, giving us the famous Einstein field equations. Now don't worry, we aren't going to get bogged down in the complex math of these 10 nonlinear equations. The absolute crucial takeaway here is how they describe reality. Massive objects like stars and planets literally bend the 3D and 4D curvature of the space-time mesh around them. Imagine placing a super heavy bowling ball right in the middle of a flexible trampoline. The mesh bends down deeply under all that weight. Well, space works in exactly the same way.
To make this a bit easier to visualize, back in 1957, the scientist John Wheeler came up with this brilliantly simple analogy. Imagine an apple and a little worm trying to get from one side to the exact opposite side. Instead of crawling all the way across the long, curved outer surface of the apple, the worm just burrows straight through the center. It takes a massive shortcut. And this beautiful, simple analogy is exactly where the term wormhole actually comes from.
So, moving on to Section 3, anatomy of a wormhole. How does this theoretical math actually build into the physical structure of a cosmic shortcut?
Well, we kind of have to shift our entire perspective here. Think about a regular long-haul airline flight. If you look at a standard 2D flat map of the Earth and you're flying from Delhi to New York, drawing a straight line directly across the map seems like the obvious shortest path, right? But in reality, planes fly what looks like a massive upward curve way over Greenland and Iceland. On a 2D map, it looks like a crazy, unnecessary detour. But on a 3D globe, it's actually the shortest physical path. A wormhole does the exact same thing, but it uses a higher dimension to create a shortcut that looks completely counterintuitive to us in our lower dimensions.
In the scientific community, this shortcut is actually called an Einstein-Rosen bridge, which was first theorized in 1935. It connects distant points in space-time. But remember, we live in a three-dimensional world, so the entrance to a wormhole wouldn't just look like a flat 2D paper hole or a funnel. Actually, scratch that, if you were in a spaceship approaching one, it would appear as a fully spherical, completely realistic 3D ball reflecting the universe around it. If you've ever seen the movie Interstellar, their depiction of a wormhole was actually heavily praised by physicists because it's remarkably accurate to this exact theory.
All right, Section 4, the white hole exit. Because actually entering a wormhole brings up a really massive practical hurdle. Now, what's really interesting here is the stark contrast. To generate enough immense gravity to tear open a wormhole's entrance in the first place, you essentially need a black hole. But we all know a black hole absorbs all matter. Its event horizon is a literal point of no return. So if a wormhole is just black holes on both sides, well, it's not a tunnel anymore. It's an inescapable trap. To actually exit safely on the other side, you theoretically need the exact opposite mechanism, a white hole. A white hole would have a strict boundary of no admission. Nothing can enter it, it violently expels matter outward, and it would shine with this blinding, extreme light.
This leads us right into Section 5, Entropy versus Information. Let's impartially look at the intense scientific debate about whether these bizarre phenomena can actually exist under the laws of physics.
On one side of the debate, we have the ironclad laws of thermodynamics. Think about the paper shredder analogy. If you run a piece of paper through a shredder, you can't just perfectly reassemble it. The universe's disorder, which we call entropy, only ever increases. Black holes basically act like giant cosmic shredders, tearing apart stars and increasing the universe's entropy. But a white hole? It would have to operate like a reversed paper shredder, spitting intact objects back out and actively decreasing entropy. And for this exact reason, a lot of scientists argue that white holes are strictly impossible because they blatantly violate the second law of thermodynamics.
But let's balance this out by looking at the opposing side of the debate, which is deeply rooted in quantum mechanics. Stephen Hawking famously theorized that black holes eventually evaporate over trillions of years. But quantum mechanics has this fundamental rule called the no-hiding theorem. It essentially states that information cannot be permanently lost in the universe. So, if a black hole swallows matter and information and then eventually dies and evaporates, where does all that stuff go? Well, many quantum physicists argue that this swallowed information must eventually be spat back out into the cosmos. And the mechanism for expelling that information, it would perfectly, beautifully align with a white hole. And here is where it gets wild. While it's heavily debated, we might have literally already caught one of these on camera. Back in 2006, the Swift Observatory observed a massive astronomical event named GRB 060614. It was this extreme white light explosion, a gamma-ray burst. Usually, these incredibly bright bursts happen when a black hole violently swallows a star. But in this specific case, there was absolutely no evidence of any star being involved whatsoever. Some scientists hypothesize that this anomalous, random explosion might have actually been a brief, real-world glimpse of a white hole in action.
I know, it sounds straight out of science fiction right now, but looking at this timeline, you can see how theoretical math very often evolves into accepted, proven science over the decades. Einstein's equations in 1915 led directly to the math for black holes just a single year later. Wormholes were theorized in 1935, and white holes got their name in 1964. Just keep in mind, it took nearly a full century for us to capture the very first actual photograph of a black hole in 2019. What starts as just purely theoretical math on a chalkboard very often becomes reality if you just give it enough time.
Which perfectly tees up Section 6, From Theory to Reality. Let's ground the final part of our explainer by looking at how modern science is actually attempting to manifest these concepts in the laboratory today.
And this brilliantly illustrates our remarkable progress, the 2015 magnetic wormhole. Now, obviously, we cannot build gravitational wormholes in a room yet, but scientists in a controlled lab successfully created a magnetic equivalent. Using a highly specialized material called yttrium-barium copper oxide, submerged in a super-cold liquid nitrogen bath, they managed to separate a magnet's north and south poles via an invisible gap. They essentially created a tunnel that routed magnetic fields invisibly from one point to another. They were bending magnetic fields in the exact same way a cosmic wormhole would bend spacetime.
So the really cool takeaway here is that human ingenuity is already finding workarounds. Even if we never harness the literal black holes needed to build a physical wormhole, theoretical models like the Alcubierre drive, which was proposed in 1994, offer an incredible alternative. It involves taking distinct steps to literally surf the space-time mesh. Step 1, you contract the space-time curvature directly in front of your spacecraft. Step 2, you expand the space-time curvature right behind it. You essentially ride a compressed wave of space itself. It effectively moves you from point A to point B way faster than light without ever technically breaking the cosmic speed limit. How amazing is that?
So, we've covered the brutal, depressing reality of cosmic distances, the totally mind-bending math of altering reality itself, and those incredibly cool lab-created magnetic tunnels. And all of this leaves us with one final profound thought to ponder today. Will we ever truly cross space-time? I mean, the equations allow it, the quantum theories support it, and our laboratories are just beginning to test the very edges of it. The ultimate future of human spaceflight might just depend entirely on whether we can find or build that cosmic shortcut. Thank you so much for joining me on this explainer. Keep your curiosity alive and keep questioning the universe.